is visually small but has a lot of data, or corresponds to a lot of data, with 1,151 shared genes, right next to another segment that only has 40 genes. So obviously this is a problem, and then it's also hard to essentially, like, if I point at this intersection here, it's really hard for you to figure out which sets participate in that intersection. And so I also showed you that this is not an isolated incident. And then we kind of took a simple data set about the Simpsons, where we had people, like Simpsons characters, and then some characteristics, which we called sets, like are these people in school, are they female, are they male, do they work at a power plant, are they evil, and so on, plus some attributes, some numerical attributes, so not set attributes on top of that. And then we had these questions that we tried to ask, and you came up with a couple of a couple of designs, and I did go through probably half of what you guys submitted, and so it was really interesting for me to see. I'll be talking about set visualization in the first half of this class, and actually, like, every major class of set visualization, somebody came up with it. So I'll always talk about the visualization first, and then I'll show you some of the screenshots from or some of the pictures that you guys drew and where they fit in. So let's take a step back and analyze Venn and Euler diagrams a little bit closer. So what is the difference between a Venn and a Euler diagram? Does anybody know that?
Euler diagrams are proportional to the size of the intersection, and Venn diagrams also include empty sets.
The last part is the important piece. Both can be area proportional, but Venn diagrams are supposed to include every intersection, even if it's empty. So that's the main distinction. So here we have a Venn diagram. Here there's the example of animals with 4 legs and minerals. And even though there are no animals that are also minerals, this intersection here is still drawn. And a Euler diagram can omit empty intersections. So here's a Euler diagram of the different nations or regions in the United Kingdom, British Isles, and so on, and their relationships, which is always surprisingly complicated. So that's the big difference. Venn diagrams for many sets, as you no doubt have figured out by now, are hard to draw. Here are a couple of examples. So the first row here shows us 4-set Venn diagrams. The second row here shows us 5-set Venn diagrams, and the third row shows us 6-set Venn diagrams. What is interesting about the 6-set Venn diagrams? What is different from, let's say, the one on the top right here? We don't have a regular shape anymore, right? These are kind of these weirdly constructed diagrams, and while they're possibly mathematically interesting, understanding what is going on in here is not really is not a good data visualization. And the reason of that is, of course, that the number of possible intersections, if you have n sets, is 2 to the power of n. So you can very clearly see that this is an exponential growth, and so therefore it's bound to fail eventually. For Venn and Euler diagrams, one problem that I showed earlier with this 6-set banana Venn diagram is that it wasn't area proportional, right? It was one of the aspects that I emphasized. So we can try to create area proportional Euler diagrams or Venn diagrams, but this is hard, and it doesn't work for the general case for more than 4 sets. So there are kind of some optimization algorithms, but finding a perfect layout is difficult. And then you also have these very small segments here, like this green segment here that corresponds to 1% and so on, and 3%. So this is simply not an ideal scenario. And so there's a couple of layout criteria that we should follow when we create Euler diagrams. Ideally, this should be simple curves. Circles are best. That makes it easy to identify which sets are participating in an intersection. And then it also kind of follows the Gestalt principle of good continuation. Remember that we had this idea when we had, we expect good continuation of shapes, and if we have these irregular shapes, we can't really trace them very well. And then area proportionality is of course also the layout criteria. So here's like what I mean with regular shapes and why this is a benefit. Like in a comparison here we have a 4-set Venn diagram with regular shapes. It's pretty easy to identify, like this is a section here, which of these sets participate in that intersection. Simply to identify because the shapes are regular. It's much harder to identify which sets participate in this particular intersection, for example here. So if you need to do this, I would recommend that you try to use simple shapes. And then also area proportionality is great, but we have talked a lot about like which of the visual channels are good and which are not so good, and we also mentioned that size is not as good as, for example, position. And so judging the size of irregular shapes is difficult. So if those two shapes here, which one is bigger? The left one or the right one? Who thinks the right one is bigger? Very few people, lots of people with good eyes. It's in fact that the left one is bigger. But this is hard to judge, right? It's not, we can't really do this with a high degree of certainty. So if we reflect on pros and cons, Venn and Euler diagram, they are, if you can use them, if you have only 2 or 3 sets, then definitely do, because they're very familiar, they're very intuitive. Like we all have been taught them in school. They're great to explain the principle of set diagrams. But they don't really work well for more than 4 sets. So you shouldn't try to use a Venn or Euler diagram for more than 4 sets. With some caveats, I'll show some techniques that for special cases it might make sense. Area proportionality is hard to do. It's not impossible, but difficult. And it's also limited to, like, for a general case, for 4 sets or less. And it's also not well suited to show attributes. Like, for example, how would you show whatever, like the attributes of an intersection here? You could try to color code it in some way, but it's not simple to do. This is a Euler diagram for where we show specific items. So these Venn diagrams that we've seen so far, they have been kind of like, we didn't see individual items in them. We kind of like had only a sum of like an abstract representation. But if you want to show the specific items, like here we have people and some kind of relationships. Think of this as clubs that those people belong to. We can see this works pretty well. So these are 2 different versions from a paper from 2010. So here we see one version where we don't duplicate any nodes, and then here we have a version where we duplicate nodes. In this version where we don't duplicate nodes, we have to create these complex shapes. So for example, the light blue one here is the shape that spans like these different areas, whereas the red one spans from here to here to here and so on. And so here the shapes are duplicated, so all of these sets are discrete and rectangular areas, and so this is easy to spot like who is in a particular set. But then the nodes are duplicated, so we see that Matthew is both in blue and in green and in orange. And so depending on the kind of task and the kind of questions you want to ask, either one has advantages or disadvantages. I think aesthetically more pleasing is probably this one. Also notice how the nesting works here. So like we have Anthony is both in orange, in red and in blue. And this algorithm made sure that you still can see the red one even though it completely encloses Anthony. So this kind of like algorithm guarantees that you always see a nesting. So here are some of your designs that are in this category of having individual items and then drawing Euler diagrams on top of it. Here with like rectangular layouts on the left and the right. I doubt this is like hand sketched. But it looks very nice, and then here in the middle we have one with irregular shapes. So that's kind of the same principle here. You can also do this on top of a fixed layout, and so this is kind of an interesting visualization technique that I do like a lot. Here we see 2 different applications for this visualization technique. This is called a bubble set. The one here are different restaurants, subway station in New York City, and here we have something like the Gapminder example where we have data about certain countries over time, and the highlighted countries are Sub-Saharan Africa. And so I'll show this video.
In this video, we demonstrate bubble sets, a method for revealing set relations with isocontours over existing visualizations. In this work, we focus on set membership relations which are independent of other relations in a dataset. Our method visualizes set relations atop existing visualizations without modifying any meaningful spatial layout. We've applied bubble sets to several example applications for which the spatial layout carries meaning separate from the set relation. Here we see a timeline populated with icons representing InfoVis publications related to visualizing communication. The vertical arrangement is determined by a force-directed algorithm to enhance set density. The individual sets represent different subcategories of data. For example, visualizations of document content are shown in orange. This prototype is interactive, allowing for a deeper exploration of the data by clicking a node to reveal a larger image or the abstract. Double-clicking retrieves the original document. When nodes are enlarged, adjacent nodes move away to remain at least partially visible. The prototype allows for interactive adjustments of the set membership. By right-clicking a set, it becomes activated. Then, by right-clicking items, they can be added or removed from the set. Bubble sets remain connected over arbitrary distances and around obstacles. Bubble sets are created by first determining an underlying virtual edge collection, which invisibly connects set members. The virtual edges are routed around intervening obstacles where possible. Set members and the virtual edges contribute to an energy field, which is used to determine the set boundary. For illustration purposes, I will turn on a visualization of the energy field. Here in red, we see positive energy areas, which should be included in the set boundary. Negative energy areas appear in blue. Negative energy contributions from non-set members allow the boundary to be pushed away. Notice the virtual edges connecting items, seen here as linear regions of high positive energy. As an item is moved, the virtual edge set is reconfigured to continuously avoid obstacles. Here we see countries represented by circles with area proportional to their population. The color of the country represents the continent. Items are arranged on a scatter plot of fertility rate on the horizontal axis and life expectancy on the vertical axis. The plot can be animated over time. By adding a bubble set over the items within a continent, we can easily see the extent of the continent within the plot. Additionally, we can find outliers which may have been difficult to discern by color alone due to their small size. Let's watch how Sub-Saharan Africa changes over time.
Okay.
This screen capture.
So I do like this visualization because I think it is effective at what it tries to do, and B, it also is pretty engaging to look at. There's two different variations on this that were published in 2011 and 2012 respectively. Line sets here are essentially a curve, a spline that is fit on a sequence of points, and so the contribution here is mostly like optimizing the order of the points. And then kelp diagrams are a variation of line sets that also allows branches, and so for kelp diagrams there's also this problem of nesting nodes, which isn't really particularly easy to see here, but we have this node here where it's both in violet and in green, and so they also make sure that the nodes, that every border is always visible. The next major class of techniques are node link techniques. The principal idea here is to treat each set as a node and treat the elements as nodes and then connect the elements that are in that set to the sets. So that's a pretty simple idea. This here is a live demo of a technique that does something like this. Here we have authors, then we have publications here, and then we have tags, like keyword tags in here. And so you could think of every data type here as a set, but you can also think of every data type as an item. But in the end, we have one person who is essentially in these like 4 sets here, in these, or in this case, in these 3 sets here, and these sets they connect to those items. And so that's a pretty straightforward way of doing that. Can anybody spot a potential problem here? What happens if I had like 2,000 nodes, for example? Yeah, so it kind of like, because we have so many links and edges going in here, it can get pretty cluttered pretty quickly. So here, to make sense of this, you actually need interactive highlighting. And you can also click on one of those items, and then it will drill down on this particular item and find other related items and so on. So this is like, this technique does more than that, but this is just an example of how you could use a node link technique to visualize set relationships. And so here are 2 examples of where I found that in your solutions. So here we essentially have a tree on top of these individual items, and here the sets, or here the characters are on a circle outside, and then the sets are here in the middle. So both of these are essentially bipartite graph visualizations that kind of follow the same principle. Another simple approach is to not show actual set intersections, but to simply show pairwise overlaps between items. So here is an example of co-mutations of genes. We see that there's Titan and P10 as the 2 the 2 biggest sets here. We see that Titan and P10 are frequently co-mutated, so like about 37 times, and that these other genes are less frequently mutated. So this doesn't show us, however, higher order overlaps. So we don't know whether like these 2 sets are almost exclusively overlapping with each other, or whether they're like part of one big cluster. So this is only an overlap between 2 different items where we don't see anything on a higher order. So we don't see, is there a mutation in P10 and EGFR that is also in TP53? That is not possible to see. However, this is of course a very scalable approach. And so here's a visualization technique that kind of took this route with a lot of additional interactions. I'm going to show this video briefly.
Intersections and preview their distributions, which one genre. First, let's explore a movie data set. Each movie can have multiple genres, a rating, and a release year. The bar length visualizes the number of movies per each aggregation. The Godfather has drama, action, and crime genres. There are many other movies and other genres. A Venn diagram is not helpful to explore the rich intersections of all genres. When we point to comedy genre, AngrySet visualizes the characteristics of comedy movies using orange preview bars, including its relations with other genres. Among comedy movies, both drama and romance are common genres. 204 comedy movies also have romance. One genre movies are common among drama, comedy, and horror movies. To explore rich relations between genres, AngrySet introduces a set matrix. Each circle includes elements of a genre pair intersection. The largest pairwise intersection has 226 movies. Comedy and drama is one of the most common genre pairs. Romantic horror movies are few, and there are no sci-fi documentaries, as there is no gray background. Let's learn more about action movies.
So here, this is the idea, and this is also like, I've shown this before when we talked about tabular visualization without the set component. This essentially allows you to explore the distributions here in a very interactive way. The next approach is, or a kind of a related approach, no, actually quite different approach, but similar, like visually similar, conceptually quite different. Here we have set matrices. So this is a technique that is really suitable for very few items. So like you're talking about 5 or 6 items, but maybe potentially even hundreds of sets. So these are actually whale sharks from the Atlanta aquarium, and which kind of chemical compounds researchers have found in their poop, in their blood. And each of these cells is one of those compounds, so I consider them to be one set. if we now like want to compare them, we can see that, for example, these two whales here don't have a lot of overlap, whereas these two here, at least up in this upper region here, they have more overlap. And then we can do kind of like explicit comparisons using and or operation. So this is really good for many sets and very few items. And so let me show you this demonstration.
In this video, we demonstrate onset, a technique for visualizing sets with hundreds of elements. In this technique, each set is represented as a large rectangle. Elements of the set appear as pixels on the grid inside the rectangle. These elements are extracted from the collection of all elements, and each element is assigned a specific, consistent position on the grid. For sets that do not contain some of these elements, those positions on the grid are empty. When two different sets are superimposed, they combine to show either the union or the intersection of the two sets. Think of the union as a logical OR operation that shows how many sets contain an element. Similarly, intersection is like a logical AND of the corresponding positions of the grid, and it shows the elements shared by all of the combined sets. More sets can be added to these superimposed sets to view common elements across all of the sets. Superimposed sets can also...
Okay, so this shows the interaction, and he's actually phrasing it a little bit differently than I did. He says, I considered this to be an item with many sets, and he like in this video, they demonstrated it as a set of many items, but either way is possible. Another example that is kind of simple are these linear diagrams. So you have like here a couple of languages like French, German, Hungarian, and people like are there any people who speak any intersection of that language? So here is a visualization in a Euler diagram of this particular data set, and here's the corresponding line diagram. And so you can see that for example, we have an intersection between French and German and Hungarian and also Welsh. So that's kind of like we can trace it here, French, Welsh, Hungarian. So this is kind of like this segment here. And so here are some examples from your design exercise that kind of show something like this. We have a matrix of, like a very explicit matrix where we have these individual dots, then two more matrix. All of those have essentially some variation of the items in the rows and the sets in the columns. And then one other approach is called radial sets. Here the sets are a segment on a circle. So this is kind of like a styled circle, not completely round. And so this is here explained with fruit and vegetables. And so the sets would be, are they fruit, are they vegetable, are they red, or are they green? And so here would be the corresponding Euler diagram. Here would be the corresponding radius set. And so we have these sets, and each of these elements, in this case, is like here we have like a pair that is both green and the fruit, and so it occurs twice, and therefore there is like one edge for this this co-occurrence, and then there's the line which is also green and the fruit, and then so there's the co-occurrence and so on. The size of these segments here encodes the size of the sets. And then this here is like a histogram, a little histogram. So we can see like here we have three fruit that are only that are yellow, so therefore they're not vegetables, not red and not green. Then here we have things that are both fruit and red or green, so they're in a two-set intersection, and then the apple can both either be red or green, so it's both in the green and in the red set. And so it's the only element, and that's why this histogram bar here is a little bit smaller. So this is a video that shows this one.
Euler diagrams offer a very natural way to depict overlapping sets as overlapping regions in the plane. However, the complexity of the diagram increases rapidly with an increasing number of sets. This is because the number of possible overlaps grows exponentially with the number of sets, which exceeds the topological constraints of these diagrams. Radial sets is a new visualization technique for overlapping sets. It avoids the topological constraints by using separate visual items for the sets. The size in each set by degree remains visible. This makes radial sets highly scalable in the number of elements. Even for large sets defined over tens of thousands of elements, radial sets gives an overview of how many elements are unique in each set and how many elements are shared with one, two, or more other sets. This quickly reveals which sets tend to have more exclusive elements and which sets tend to share elements with one or more other sets. Moreover, the histogram bars can be colored according to an attribute of the elements they represent. This reveals how this attribute correlates with the set memberships. Likewise, the links can also be colored by an attribute of the overlaps they represent. For example, we can easily find out which overlaps represent a higher disproportionality. The elements aggregated in the bars or in the links can be explored in detail using interaction. An overview plus detail interface shows details about the selected elements in a tabular list. The attributes of these elements can be analyzed further in additional views. Also, radial sets highlight the portions these elements represent in the sets and a chart.
So,
besides intersection, these modifiers allow.
They also try to do higher level set intersections. Let me see. But then it gets a little bit, let's say, crazy. So, like if you want to show like higher order intersections, like they develop a new set of glyphs and so on, but I find them a little bit hard to read. And surprisingly though, this was one of the most frequent visualizations that you guys drew. So here we have, like, these are all variations where like a set is represented as somewhere as like one big node, and then the strength of the connection corresponds to the relationships between them. And so here are some different examples, and I actually even, like this one even has histograms for age built in, so it also shows attributes. And so like of course like this here is probably closest to what, or those two here, like this one and this one here are probably closest to the actual layout that Radial Sets uses. This is just like a linear version of it. So yeah, it's interesting that this was kind of one of the most picked visualization technique. Okay, and so next I'm going to talk about like a little bit more in detail about one of this project that we did in 2014, and I kind of like also gives you a little bit of a more deeper dive into why did we do this and what are the kind of questions that we try to ask. So we built this set visualization technique here with the goal of developing efficient visual encoding. So instead of having these arbitrary shapes, we wanted to use position on a common aligned on a common scale for our visual encoding. And then we wanted to be able to create complex slices of a data set. So we wanted to like not only use this as a set visualization, but also as a query tool into a data set. And we wanted to visualize attributes about these intersections. And so this is a visualization technique that we built. We call it upset. And I'll walk you through this in a little more detail, but it has three components. It's the visualization of the sets, visualization of properties, and then visualization of the elements, and in particular element lists and queries, and then attribute details. So how does it basically work? What we do is we use a matrix layout where we have like here sets A, B, and C in columns. These bars encode the absolute size of these sets. And then we encode in this matrix with these like filled in cells are participants in this intersection, and empty cells does not participate. So we start out with this like empty row that it corresponds to all elements that are in none of the sets. Then we have the row that corresponds to all elements that are in A, not in B, and not in C. Then we have the elements that are in B, not in C, not in A, and then only in C correspondingly. And then here in this matrix we show this A-B connection like this with two filled in the connection. and similarly for A and C, and for B and C. And then finally the 3 set intersections. So now we have a matrix that essentially identifies each of these intersections uniquely, and it's kind of easy to read which sets are in which intersection. And then we can plot the cardinality or the size of these intersections here in detail using bars, and in this case also labeled. So you can see that there's 5 elements that are in none of the sets, and there's 20 elements that are in A and C but not in B. And so what is neat about this is that we can now, by using this linear layout, we have space to plot additional data. So for example, we can calculate a statistical measure of how surprising an intersection is, given, for example, the assumption of a random distribution of sets. And so here we would see that just A is a little bit smaller. And so what this, smaller than this would expect. And so what this is mainly about is, if you have sets of different sizes, you would expect the 2 sets that are very big overlap a lot. And so here, A is rather big, and so you would expect it to have more elements by itself. Or you could ask also, what is the distribution of an attribute in an intersection? Think of this like as the age for the Simpsons characters. Like, what is the distribution of ages in a certain cell? And that could be easily plotted in a box plot here on the side. So this is the implementation. This is a web-based tool. It's implemented in D3. This is again the movie genres data set. We have comedy, drama, action, adventure, and so on. And so if you look at this, we see that comedy and drama is the biggest intersection, which is kind of surprising because comedy and drama, intuitively, those two don't go so well together, right? And so if you look at this statistical measure of how surprising it is, we would actually, this is actually smaller than we would expect. So our intuition was right. But why is it still so big? Well, it's because comedy and drama are very popular movies in the, movie genres in the first place. So those 2 sets are really very big, and therefore the intersection between those 2 is pretty big, but it is still smaller than we would initially expect. And if you look at the attributes here between comparing, for example, drama-comedy combination and action-comedy combination, we can see that drama comedies are on average rated higher than action comedies, which is again not very surprising because action comedies are not really known for their high quality. We can use this interface, like any tablet interface, to ask questions based on sorting. So we can ask questions like, which is the biggest intersection, and simply sort by cardinality. Or we can ask a question, like, which is the most surprising intersection, and then it could sort by deviation, as we can see here. Or we can sort by any of the sets to see all of the combinations of that set in detail. Or in this case, we're sorting by degree, so like first 1 degree, 2 degree, and so on. So this gets a little bit more interesting if we start to think about aggregation. So we can ask questions like, are many items shared between 2 sets? And then we can do aggregate by degree. And so we introduce a new visual encoding here, where we have, for each degree, we have like a separate bar here. We see degree 0, there's only 1 element. Degree 1, there are 3 elements in degree 1, and this bar here corresponds to the sum of its children. So, of course, like the same we do for degree 2, so this is the green segments here, and then for degree 3. We can also ask, for example, how are the elements of B distributed, and then simply aggregate by set instead. And so in this case now we introduce duplicates. So we have the none, all of the A's, and then all of the B's. So there's a couple of things here. We introduced a new visual encoding. First, so there is this like little dot here, which essentially encodes may. So this is kind of like a logical qualifier. It may or may not. So here A must, B may, C may. And that kind of like is the query that corresponds to all of the elements in here. And then another problem that we see here is that this bar has gotten really big. Like one approach would be to use log scales, but since we have different things at different scales, we still might want to see like variation at smaller scales. So instead we kind of developed this horizon bar here, where the bar wraps around. And we played with this, and you can wrap it around up to 3 times, and it's still pretty readable. And then we have duplicates, obviously, which kind of means that some of the elements here are not on the screen, and so we can deal with that, for example, by using aggregation. So we don't actually have to see every element that composes something. And so here's how that looks like in the technique. So this is aggregated by sets. So we see all the comedies. Here you see this wraparound bar with this flexible scale, and then we can collapse comedies. We can then aggregate on the second level to aggregate first by sets, then by overlaps. And now this bar here corresponds to all the comedy dramas, and this shows us how these are composed in detail. We can then specify queries into the system, and as I mentioned in the filtering and aggregation lecture, the queries are always a good way of dealing with a big data set. And so you can essentially choose from these options, must, may, and must not, and then the system will give you a query result. So you can kind of generate those queries dynamically. And we can also do logical combinations, but I'm going to skip over this. So here is all the movies that are action, adventures, and children movies combined. And so we see there are 6 movies that match that particular query. And then we can click on this bar and see which 6 movies are that actually. Okay, so then I kind of want to walk you through a couple of examples here. How do documentaries, for example, compare to adventure movies? So we have the documentaries here at the bottom. And so one thing we see about documentaries is they don't mix much with other genres. So they're kind of isolated by themselves. There's not a lot of children's documentaries. There are not a lot of crime documentaries and so on. If we look at, here we can see the details about these documentaries. And then here is a plot about those elements where we plot release date on the x-axis versus rating on the y-axis. And what we see is that those documentaries are on average pretty highly rated. So let's compare this with adventure movies. So the first thing we see is that adventure movies, they kind of mix a lot with other genres. There's many, many different combinations. And then we see that the rating of the adventure movies is much more diverse. There's a big cluster of lowly rated elements here. And then we can also see that historically the adventure movies seem to have been better. Anybody has a guess why that is? So I don't know for a fact, but it's very likely that this is a data collection bias, right? This data set was collected in internet times, and so it's unlikely that people go back and rate really, really bad movies from the 1930s. So there's the movies that are good, we still remember them, we still talk about them today. So therefore this is a data collection bias where we see a very clear trend that all the movies are better. This doesn't necessarily mean that everything nowadays is worse than it used to be in the good old times. It means that we don't have data about the good old times. We also built an R version because we observed that this is a pretty popular thing in the bio community. And so one thing that I wanted to note here is that we chose to flip it around because these figures that people create with the R version are usually made for publications, and there the wider format works better than the high format, which works better for scrolling. And so this was one of the design adaptations, and then we have other details that were changed. And so now we can look at the banana chart and see how that looks like with this visualization technique with Upset. And so while we couldn't really tell much about this visualization technique, there's a couple of things that we can clearly spot here. So first we see that the combination of all of these 6 plants is by far the biggest intersection. So those plants have more in common than they have differences. And then we see that these 3 down here, they are the second biggest intersection. And then the third biggest is a combination of these 5 plants. And so this top plant here is the date. And so we could reason here that the data is probably the most different from all of these other plans because of what we see and how it is kind of separated out from everybody else. So this is kind of like an informative visualization that follows good data visualization design principles and is not just like something nice to put in your paper. And of course somebody has come up with this idea in our redesigns too, so this is one of the pictures that I took from your submissions. Okay, there are tons of other options. One of the recommended readings is a summary, like a state-of-the-art report on set visualization. Here is a website that kind of collects all of these different set visualization techniques. There's really many, and it's been a popular research topic in the visualization community. So I didn't cover everything, but I think I covered a couple of representative classes. Okay, so next I want to do a design critique. The design critique here is on multidimensional scaling and networks. Look at the colors are pretty consistent. So it's just like positioning codes, the colors just encodes redundantly. Like the position on it doesn't encode something. Let's talk about this. Okay, so I've got a lot of questions. So, what is the data that we see here?
Who influences who and how?
okay, who's who?
Bands or music.
So we have some kind of like artists, right? We have three different types of artists. These are musicians, painters, or philosophers. And so what data do we have about those let's say artists in general?
Music.
No, I mean, what is the data that is encoded here? It's not just they exist, yes, but what do we know about them?
How
The
they
significance of the,
Like one after, like, please raise your hand.
the significance of the respective person.
Yeah, so how important they are by some measure in terms of how is that encoded?
The size of the circle.
The size of the bubbles. Okay, so what other data is there?
by what sources are they influenced?
Exactly. So there's influences. Like none of the artists, of course, exist in a vacuum, right? So everybody is being influenced by somebody else, and in turn is influencing them. How is influence encoded?
By the lines.
Exactly. So I have to click on one, and then I see lines. Let's do something that is a little bit easier. And so what are the two types of edges that we have here?
Like who influenced that artist and that artist influenced who in turn.
Exactly. And so that's encoded using different edge types, right? We have this long tapered edge here, and for being influenced by, and these edges with arrows to show influences. Okay, so why do you think this visualization doesn't just show all of the edges?
It's going to be crowded.
Exactly. So what you have to do is you have to use interaction to reveal the relationships. It's already pretty cluttered if only for one selected element, right? So what else is the data? What other data do we have here? Like what is the most important mark and the most important channel, the most important visual variable?
Area.
Position. But area is second most, but what does position encode here?
Similarity.
Exactly. So this is a multidimensional scaling applied to the these artists, and so then you could argue that groups that are in a similar region are also similar to each other in terms of style. So we see the Beatles here at the center, next to it, like the Rolling Stones are at some distance. If you go further out from the Rolling Stones, you go to Elvis Presley. Down here, like Jimi Hendrix. So let's say up here we have Roxy Music, Pink Floyd, and The Who. So kind of that intuitively, if you know a little bit about music, that does make some sense, right? So we have maybe some temporal trends here that more recent bands are on the right and a little bit older bands are on the left, but it's not necessarily that's not necessarily the encoding. That's maybe just like one thing that shines through here. What other data is encoded? So I got the question, what does the color mean?
Probably genres of similar fashion.
Yeah, so the color is really just a redundant encoding of position. It's kind of like, you see that there's very continuous, very gradual changes. So the color here essentially just reinforces these similarities, I would say. And then we have one more data type that is only visible in this view. Time, yes. So when was the band formed? And so if we click on the Beatles, what is interesting about this?
It's influencing almost everything.
That's true. And what's even more interesting?
Bands who were before Beatles.
Exactly. The Beatles are influencing artists or bands that formed before the Beatles were formed. So you can see that there's like, of course, this is the time they were formed. And then this would be interesting to see over like how long their careers lasted. This is an information that we don't really have here, right? And so how are these edges routed here? For earlier we had the edge types, but here we also have the positioning of the edges, right? So influences are at the bottom and is influencing is at the top. So this is like a clear separation where therefore like we don't have any edge crossings, and so this is kind of like a way less cluttered view. And we can see that like people like David Bowie have the same patterns. He's influenced by people who started their career later than him, and then he's influencing people who started later. What is interesting about the scale here? I think it's a little bit more pronounced with philosophers. Is this, like, what's the time scale?
The time scale of the left is really compressed.
Yeah, so it's completely nonlinear. It's not even probably some logarithmic, or it's just like a function of where those nodes are placed. And they essentially encode that by showing these many axes here. And of course, for philosophers, this makes sense, right? We have Plato in the antiquity, again, being a classic Greek philosopher, but then we still know a lot more about like philosophers since the 1900s. So there's like, we have roughly like a third of the space here for philosophers after 1900, and then there's another like 2,000 years here on the left. Which of course also again makes sense because of how we remember historic figures, and it's our memory for recent times is much shorter. How do you think you could collect a data set like this? Like if I told you, do this as your class project, how would you approach this?
Maybe this is overkill, but for the music you could do spectrographic analysis and similarities.
That would be really fancy, yeah? Other ideas?
Just go to Wikipedia and then look at like one person's page and see who they're
Exactly. Do some kind of link analysis, right? You can do some text parsing, like was influenced by, and then you have the names of those people that were influences. You can follow those links, and then you can retrieve those people. So it's like a pretty standard web crawling problem.
But how true would that information be?
Yeah, that's a good question. Like how accurate is it, right? And it's clearly not going to be completely accurate, but this is also in a domain that is inherently not completely accurate, right? How similar are to artists is probably something that you can debate between two experts for a long time. So the question is, in a data set like this, where we don't have like ground truth, where we kind of show something that is pretty abstract in its first place, can we kind of afford to have inaccurate data like this? And I think you can, but there's a lot of research, for example, trying to use Wikipedia for various reasons, right? To kind of like learn something. So I know one project that is at the MIT Media Lab that tried to quantify the cultural output of countries based on Wikipedia. So they kind of like look at, like, for example, important people, people like Albert Einstein. They measure how important Albert Einstein is by measuring how many language versions of Wikipedia have a translation of this person. And so for Albert Einstein, he's probably going to have an entry in almost every language, right? Whereas some like country singer from Arizona might probably only have an entry for like an English and maybe a French Wikipedia, but might not have like whatever Polish Wikipedia entry. And so there's various ways of developing those metrics and of developing like these kinds of data. And so these kind of research projects, they're kind of an interesting hybrid of data collection, data aggregation, and data visualization at the same time. This particular visualization, I think, is based on Freebase. Freebase is a kind of like something similar to Wikipedia, but is more structured. So it's more of like a graph representation. And you can like download that, and there's been kind of a few visualization projects done with this. So, anybody want to give their opinions? Do you like this visualization? And why?
I like it because it shows something that can be really intuitive to you as a human once you see, you know, like if you know any of these musicians, you can kind of understand the connection between them. I don't think it's super intuitive to understand what it means. Like,
Yeah.
I kind of had to take a leap to guess that, you know, like the position was encoding similarity.
That's true. Any other opinions? So I kind of want to say something about the group that does this. Marian Dirk, he's a professor at Potsdam and did a PhD in Calgary. And so he's following this concept of informal information visualization. He kind of like coined the term the information flaneur, just somebody who is browsing and kind of like consuming visualization not to make a decision based on which, like for example, which stock to buy, but kind of like for people to enjoy, to play, to experience. And so like most of his visualization are in this style. And I think if you like, I think that this one is very successful. I enjoy playing with it and seeing how are the things connected very much. Like I personally like this visualization a lot because we kind of like, on the one hand it does, like for me, like I know most about musicians, I guess. It kind of like is interesting, even like it could be nice to have connections here to some like thing like Spotify, right? That you can see, okay, those people here are similar. Let me like listen to a couple of those tracks. That kind of like as a discovery mechanism itself. And so I do appreciate that, and I think it's kind of well done. It does not really explain the positioning. That's clearly a valid point of criticism because it has nice legends for everything else. So it could do that better. Anybody else want to share an opinion? Okay, so if not, let's move on then. I think we're also moving into a kind of related area, into something that is a little bit fuzzy, because it is just really hard to do. That's text and document visualization. So why is this important? What is the thing about text and language? So language or text is very abstract. So we don't really it's not neatly classified into bins. It's kind of this very unstructured data set. So remember in the very first, or in one of the very first lectures, we talked about data types, and I mentioned that there's structured data like tables and graphs and meshes and grids. And then there's unstructured data like video, images, and text. So text is one of those unstructured data sets, but it's a little bit more structured than video, right? So we know we have rules of how we write, we have grammar, we have relationships between the words, but those are very complex. So it's abstract, it's general, but it's also extremely expressive because it is essentially the medium that we use to communicate about everything, right? It's much more expressive than visualization because speaking simply, like speaking or writing can essentially, ideally express every possible idea. However, it's also pretty different across population groups, countries, accents, religions, and so on. There is lots of ambiguities. One thing that is different for text and speech than for visualization is that we perceive it only linearly. So we have to read from A to Z. We can kind of skim sometimes, but mostly we perceive it linearly over time. And as I already mentioned, text is semi-structured. We have grammar, we have words, we have sentences, we have paragraphs, we have documents, we have volumes, and so on. So there's like hierarchies and structures that we sometimes can make use of. And then of course the appearance does also vary by typography, calligraphy, and so on. And so why do we actually care about visualizing text? So if we look at data growth, we can see that this structured data compared to text data is still like a minority. Text data in the form of like just plain text or log files or whatever outgrows structured data sources by quite a bit. And so obviously this is an important data resource. A couple of words about typography. Like everybody is probably aware of that, but I just like think it's important to think about that too. There's different typefaces like serif, sans serif, bold, italic versions of typefaces, point sizes, line length. There's alignment, vertical alignment, horizontal alignment, spacing between groups of letters. And then we have things like kerning, spacing between the letters, and then there's also special cases of combining letters to ligatures, like as we have here, FI is combined into this ligature. And these are just some kind of typesetting things that are interesting to know about. Why I wanted to say this is like creating a font is an art that requires profound design knowledge. And you might remember the fat fonts that I showed, which was kind of like a hybrid between data encoding that encoded by the darkness of a character, of a number, and this actual representation. So that's kind of like an in-between things. And like how you choose your type font can of course influence your message. Comic Sans is like people complain a lot about Comic Sans on the internet. This is the presentation of the Higgs boson, which is arguably one of the most important scientific discoveries in the last 100 years, or in the last 50 years, and it was presented in Comic Sans. Like, why do you do that, right? There's like presentation matters, but of course it doesn't matter to everybody. But clearly, like this slide has a couple of other things that are wrong with it too. So let's go a little bit more into visualization. So first we have visualization for raw text. Like in daily use, we use kind of things like images and font sizes and headlines kind of to give us an idea of how a document is structured. Or we have things like overview plus detail. Here is like a screenshot of a typical PDF viewer where you have like a detailed view and an overview where you can quickly navigate between pages and then essentially see the document, like the images and the paragraphs and so on. And then we have, we highlight semantics in things like code editors here, where certain structures are like highlighted with a color. If you go into a little bit more esoteric spaces, here are visualizations for raw text. This is like a historic technique, the document lens, that kind of does like a geometric distortion of a document. So what do you think about that? Is that a good visualization technique? Would you like to have something like this in your Kindle? Would it make your reading experience better? Probably not, right? You don't really care how the text looks like 3 pages from now. You care about the content, so you have to have some linear structure. So this is like, I think, this is from 1993, and back then, just doing such a geometric transformation was difficult, and so therefore it's probably a paper, but it doesn't make a ton of sense as a visualization technique. Here is a visualization of search results, and so of course if you search something, I don't know how that happens to you, it happens to me a lot that I search something, and then I don't find where that word is that I searched for. And so I keep scanning, and then it doesn't see it, and so kind of this technique intends to fix that problem by also increasing the font size of the search term and neighboring terms. And so this is like, does it actually for PDF documents, which is technically also pretty challenging. But so more generally, like this was all not using any structure of text. More generally, what we want to do when we visualize text is we want to convert unstructured text into some kind of structured form. The simplest way of kind of doing this is simple counts, like a bag of words, that you can, for example, use for a similarity measure. You kind of like build up a histogram of all the words used, and then you have like words like princess, dragon, and castle, and all of these words occur in document 1, and only castle appears in document 2. And now you can make a reason about how similar those two texts are, because if two texts share a lot of words, then they might be actually also similar with respect to content. However, there is usually a lot more involved, and there's like a dedicated lecture on natural language processing, obviously, which is kind of contains many of those concepts. and even more. So if you want to extract features from text, we kind of need to clean it. We need to do sentence splitting. We typically also do changes to lowercase. We do stop word removals because very frequently the and he and she and so on, words like this is going to be dominating your text. Then it's stemming. So stemming is this process of essentially removing any kind of like extraneous elements of a word, because we have declinations. For example, weakness is like if we stem it, it would be stemmed to weak. Or yields, it would be spelled to yield, and so on. And so this is like an algorithm for stemming. And so this is not, of course, super readable anymore, and I don't think this is the best stemmer out there. But it's kind of like illustrates the process. Then parts of speech analysis. This is essentially where we kind of try to understand what are, like, here is a demo for parts of speech. Here we try to understand the grammatical attributes of each of these words. So we have like preposition, we have singular nouns, we have a proper singular nouns, predeterminer, and so on, an adverb, an adjective, and so on. So the parts of speech tagging is a hard problem, but can often be used to extract things like, for example, if you would want to do sentiment analysis, you might care about adjectives. And if you want to visualize sentiment about a topic, then you might want to do some parts of speech tagging, extract the adjectives, and then kind of learn about like what are these positive or negative, and then represent that in some visualization. Other things are non-chunking, name entity recognition, but also like deep parsing or trying to understand text, which is like getting better and better recently. But of course, text features are complicated. Here are a couple of examples. Toilet out of order, please use floor below. Or one morning I shot an elephant in my pajamas. How he got in my pajamas, I don't know. Or did you ever hear the story about the blind carpenter who picked up his hammer and saw? All of these are complicated text structures that are not easy to automatically parse. But again, for visualization, like, we can't expect this to be exact. So maybe just for some topic analysis or for some getting an overview, these kinds of problems are not terribly significant. So if we look at like text units, we start from the very top, or let's start from the bottom. We have the smallest unit, which is a letter. Then we have words, then we have word groups, sentences, paragraph, section, chapters, documents, document clusters, like a whole corpus, or a corpus of corpora. So this is like where different visualizations play a role. You have linguistic visualization. For example, my colleague Maran Maya did a project with Nina McCurdy, did a project on sonic patterns in poetry. That would be very low level here on the letter and word level. When you want to understand the content of a single document, you're here in this blue space. And if you want to understand like what does like this collection of documents in the Library of Congress mean, then you kind of probably want to have some higher level representation of what types of documents are there and so on. On the text level, the Wordle is probably one of the most popular text visualizations out there. Like a Wordle is essentially just like word counting and then rescaling a word based on its frequency. And like you've probably heard of tag clouds. A Wordle is a variation of a tag cloud. So words that occur often are shown in large, and then you can vary font type, size, color, and so on. And so there was this great website where you could actually create your own Wordle, and I kind of wanted to demonstrate this, but it uses Java, and Java is now discontinued on all modern browsers, so this kind of visualization cannot be used anymore. But you can see that a couple of examples here. So you could choose like your font size, your alignment, your coloring, and so on. And so you would get things like this here, and this is like a comparison of two pieces of text. This is Barack Obama's speeches, the Democratic Convention in 2008. One's visualized with a Wordle, and one's visualized with a tag cloud. Which is more engaging? The tag cloud is more engaging?
I like the word.
It's subjective, right? I can't really say no, but I disagree on a personal level with that. So the word kind of like, it makes better use of space, right? It looks better, it's more engaging, it's more interesting. The tag cloud conveys the same thing, but I like this description that it always looks like a ransom note. Like somebody has stitched together words from different newspapers. So, and then you can also style word clouds in various ways. There are now algorithms to give it some background image and then only place it in this area and so on. So this is just an example what you can do. And maybe let's just leave it here because I'm gonna get into like structured text analysis, which will then continue after Thanksgiving. Happy holidays, everybody, and I'll see you back next Tuesday.